In this lesson, we're going to start to look at the normal distribution. Now, the normal distribution is a continuous probability density function. It's often called the bell curve because of its bell shape. So here we have an example of what could be a normal distribution. You'll notice it's symmetrical and the mean, median, mode all occur at the same point. If our data is positively skewed, i.e. stretched out to the right, the mean will be dragged up. Okay, the median will be dragged up slightly, if at all, but the mean definitely will be bigger than the median and the mode. If we have a negative skew, the mean will be significantly dragged down and the mean will be less than the median and mode. So our aim basically is for our data to have a normal distribution because then we can interpret it a lot better than if we don't know what the shape is. Now, the equation of the normal distribution curve is this guy here. Pause the video and have a look at it. You can see it's quite complicated. More on that later. Now, it's really difficult to find probabilities associated with that. You imagine trying to integrate that. It'd be a bit heavy. So we often use technology to do that, or we use tables of values for what's called the standardized normal distribution. So the standardized normal distribution, we set the mean equals to 0 and the standard deviation equal to 1. And this is what we do when we talk about Z-scores. So recall, well, we've talked about it a little, Z-score tells you how many standard deviations above or below the mean a score is. For example, if you have a Z-score of -1, this tells us that the result is 1 standard deviation below the mean. And a Z-score of 2.5 tells us it is 2.5 lots of that standard deviation above the mean. So we often use for the standard normal distribution the letter Z, hence the term Z-scores. And you can see it simplifies a bit, yeah, our probability distribution function. The graph's still a bell-shaped curve, but the maximum is at Z equals 0, the mode, i.e. the Z-score right on the mean. So the mean will be 0 and the standard deviation is 1. Interesting though, the points of inflection are each 1 standard deviation from the mean. So that's an interesting feature of the normal distribution. Now that seemed all fairly complicated, but in reality, it's fairly simple here. So what we want to do is use the tables, which are at the back 2 pages of your booklet, to find the probability that a Z-score is less than 1.05. So recall that it's a cumulative probability distribution function there on the back. You can see from the shading. So all our values will be less than or equal to. So this first question's fine. So the first table you see are for negative Z-scores, so I don't need that. I'll need to go to the positive Z-score. And I'll need to find the Z-score of 1.05. So we'll go down to 1.0. So it'll be 1.00, 01, 02, 03, 04, 05. And you can see we have this value here, 0.8531, and that's our answer. Now, it doesn't matter if it's a less than or equal to because it's got that same feature of continuous probability distribution function that the probability of any particular value is 0. So we're just going to jump straight to the negative 2.03. So we've got the negative ones this time. We go down to negative 2.0 across to 3 and we have that value of 0.0212. Okay, so if you're given a negative Z-score table, that's what you'll need to do. However, quite often you'll only be given the positive values. So you'll only be given that second part of the table. So what will we do in that case? Well, we can work out the Z-score of 2.03. So we'll actually work out this. Now by symmetry, less than negative 2.03, is this value, which is the same as greater than 2.03. So we'll just rule that off and this is what you will need to do if you're not given the negative values. You'll need to do 1 minus the probability of the positive value. And you can do whatever you want. Actually, technically, that should be a less than, but we'll just leave it as so. So your z-score will give you this in the table, and so 1 minus it gives you this, which is the same area, same region as that. So if you grab your table and look up 2.03, I'm a bit sick of going back and forth, you should see 0.9788. So we would do 1 minus 0.9788 and we get the same answer. So as I said, you may not always get the negative table. How do I work out the probability of something being greater than 2.05? Well, my table always gives me less than, so I'll just do 1 minus the less than 2.05. So again, grab your table and look up 2.05, and I've got 0.9798. So we'll go 1 minus 0.9798, which gives me some answer. So let's check that together. .0202, so a little bit more than 2%, okay, 2% chance. And then our final type is when you're asked to find between two areas. So basically we want it between 1.05 and negative 1.05. Now in this example, these two are the same. That won't always happen. So how would you do it if they, let's pretend they aren't the same, and then maybe we'll talk about tricks if they are the same. Well, obviously you need to do the big one minus the little one. So you'll need to work out each separately and then minus them. So if we go to the 1.05, the positive, 0.8531, and we're lucky enough to have the negative scores today, so we're going to use that. However, I'd have to do 1 minus the positive if I didn't have that. So now go down to negative 1.05, and I've got 0.1469. Note that would be the same as 1 minus that guy, using sort of the method we used in part 2. 169, and we've got 0.7062. So there's your first type of questions that you'll be getting on z-scores. Given a z-score, use a table to find the probability. You might also be asked to calculate and compare z-scores. So as we know, for example, in our tests, not all our tests are of the same difficulty. And if it's an easy test, you need to get a higher mark. And if it's a harder test, you don't need to get as high a mark. You just need to beat more people. So this leads us to z-scores. So to calculate your z-score for any task, you're going to get your mark, I'll put the first one in here, minus the mean, which is 49 for assessment task 1, divided by the standard deviation. And because they're all in percentages, I don't need to do any converting. Usually with the z-score, we go to 2 decimal places, and I get negative 0.33. So you can see in the first task, they were a little bit below average, but that's fine for extension 1, isn't it? So we'll repeat for the next one. So grab your calculator, set up your fraction first so you don't stuff up your order of operation. Do your mark, 60, minus the mean, 65, and divide that by the standard deviation of 20, and we have negative 0.25. So still a little bit below average, but a bit better. We're getting closer to 0. We're getting closer to average. And finally, 53 minus 51, all over 18. And we have positive 0.11. So you can see in assessment task 3, they've actually gone above average. Now to find their percentile for each task, that just means the percentage of people that they beat. So if you get your Z-score table up again, and the first one we're going to go to negative 0.33. So find that, and hopefully you have 0.3707. We'll do it as a percent, so 37.07%. So that's their percentile. That's how many percentage of people they beat. So repeat that now for negative 0.25. And feel free to practice using the positive one where you have to turn it around as well. And we have 40.13%. And finally, positive 0.11. So go to the positive side and we'll do 0.11. And you have 54.38%. So basically it's the same as the probability, except we just put it as a percentiles. Okay, so then part C says which tasks did they do best in? They did best in assessment 3. And you might be asked to justify because it had the highest Z-score. So although you think, okay, the mark in assessment 2 looks the best, relatively, they did best in assessment 3. So that's a very common type of question. What comment should the teacher make during the parent-teacher conference? Well, some sort of statement that although they started off the semester slightly below average, not that there's anything wrong with that in extension 1, that they've been improving. So something about improving, and obviously, justify it in your HSC. As you can see, their Z-scores have been consistently getting better to the point that they're now above average in extension 1. Part E, if they wish to obtain their relatively best mark in the trial HSC, which has a mean of 60% and a standard deviation of 12%, what mark will they need to beat? Well, they need to get a Z-score bigger than 0.11, and I'd leave that on my screen because you'll just have some rounding errors otherwise. It was 1/9 if you convert that to a decimal. Well, their mark needs to be greater than 60 plus the Z-score, ... times the standard deviation, because remember, the Z-score is how many standard deviations you are above the mean. So we'll go 60 plus 1/9, I'm going exactly. So they'll need to beat 61.3 or higher. You might want to round it to 62%. It depends on the question. Therefore, higher than 61.3%. Okay, to get their best mark. Okay, part F. Nessa's going to scale all the marks to a mean of 72 and a standard deviation of 15. Okay, calculate their scaled mark. Let's go to the nearest percent for each task. So all I need to do is basically I want the average to be 72, and then we get their Z-score, which was 0.33 repeater, times the standard deviation. So 72 minus 0. Put a few threes in there, and we get about 67%. Repeat with the next Z-score, so it's 72 minus, that was a neat one, 0.25, times the new standard deviation we want. And that one will scale to 68% to the nearest percent. And finally, in the last one, we'll go 72 plus, because we've got a positive Z-score, 0.1. I put a few ones in there so I don't have rounding errors, times 15, and we have 74%. Okay, I'll just write that in. Times 15. Or use your 9. Now finally, we're going to look at the empirical rule. So for a normal distribution, we have the following proportions, and these are on your HSC formula sheet. So you should spend a little bit of time now trying to find that. There will be 68% of scores lie within one standard deviation of the mean. So if we get the z-scores between -1 and 1, 68% of people will lie between that. And then you could halve it and find that, there's 34% between each. The next piece of information you're given is 95% lie within 2 standard deviations of the mean. Now, a lot of people then break that down further. So if you do 95 minus 68 divided by 2, you'll get 13.5%. And this tells you how many lie between 1 and 2 standard deviations. And finally, this is when you're almost certainly going to lie between these, 99.7% lie between -3 and 3. How did they get the little 2.35? Well, they just went 99.7 minus 95, divide 2, and they'll get 2.35. Now, there's a little bit missing here. So if you do 100 minus 99.7, divide 2, I think you get 0.15. That means that 0.15% of people get above 3 standard deviations, and 0.15% of people get below 3 standard deviations from the mean. Okay, so we can use that without our tables to work out proportions between certain z-scores, but they've got to be integers. So the first one here asks, what's the probability or proportion between -1 and +1? Well, that's straight from the information, 68%. Between 0 and 2, well, I know between -2 and 2, it's 95. So I'm just going to divide that by 2 and I'll have the answer straight off. 47.5%. Some people prefer to work out these little percentages before they even start their test, and they'll just add up 34 and 13.5 and get the same answer. It's up to you. Okay, what about below -2? Well, I know between 2 and -2, that's 95%. So if I do 100 minus that, I know 5% lie outside -2 to 2. And then I just need to divide that by 2 because I want the bottom tail, 2.5%. Or, as I said, you could have just added up 2.35 and 0.15. It just means you'd have to do that before you start, any question. Okay, what about between -1 and +2? Well, from -1 to 0, it's half of 68. And from 0 to +2, it's half of 95. And then if I add them up, I'll have the percent that I need. 81.5%. Or, as I said before, you could add up 34, 34, and 13.5, and you would get the same result. Okay, you have a go at the next two, and then we'll check those in class together. Now let's have a look at an application. With all our applications, our first step is we want to get the z-score. So to get the z-score, get the mark minus the mean divided by the standard deviation. Do the same for the other one. Mark minus mean divided by standard deviation. So this question is just saying, what's the probability of a z-score between -1 and +1? Okay, because that's a -1 z-score and a +1 z-score. And we know that's 68%. That's the percentage of adults that should lie between that. What about more than 178? So I want to know the probability of greater than 1. Personally, I always have my little sketch, but you'll have it on your formula sheet. 0, 1, I want this. Well, I know this is 34%, and each half is 50%. So option 1, I could do 100 minus the 84%, or I could do 50 minus the 34%. That's up to you. I might go the 100 minus the 84, and I'll get 16%. Okay, sometimes it's good to have two ways just to double check. Okay, final example, we have a random sample of 200 adults, and we want to work out how many of those expect to have a height between 146 and 194. So again, let's work out the Z scores first. So 146 minus 170, and we have -3. Again, let's work out the Z score of the top. And I think that's going to be +3. So that will be nice and easy for us. So we know that the probability of being between -3 and 3 is 99.7%. So I just need to do 99.7% of 200 adults. So that will be just that times 2, really. So 199.4. So we would expect 199 adults out of the 200. Okay, same thing. You have a go at that one and we'll check that in class.